So, have you ever wondered what it's like to be a detective, but, in the digital world? Today, we're going to step into the shoes of the investigators who hunt down the most dangerous software on the planet. Welcome to the world of malware analysis. Let's open up the case file and see what secrets we can uncover. Think about it. Every malicious file is like a locked room mystery. It's built to do harm, but all its secrets, what it does, who it talks to, how it hides, they're all sealed up inside. So the number one question for any analyst is this: how do you get a confession out of a piece of code that could literally destroy your computer the second you run it? And that's exactly where malware analysis comes in. It's this incredible field that mixes digital forensics, reverse engineering, and, let's be honest, a healthy dose of suspicion. You really have to think of it as digital detective work, where every single byte of data could be the one clue that cracks the whole case. All right, so every good detective has a playbook, right? And in malware analysis, there are two main ways to tackle a case. First, you've got static analysis. This is basically examining the crime scene. You study all the evidence, the code, its structure, any text inside, without ever letting the suspect make a move. And then you've got dynamic analysis. This is the stakeout. You let the malware run, but you do it inside a totally controlled, safe environment, and you just watch its every move. So let's start with phase one, examining the scene. This is where we gather our initial intelligence using static analysis, looking for clues without putting our own system at risk. Okay, so one of the very first things any detective does is check what kind of tools a suspect is carrying. In the digital world, that means looking at the imported functions. These are basically built-in Windows abilities that the malware is planning to use. It's kind of like finding a set of lockpicks in a burglar's bag. It tells you a whole lot about their intentions before they've even done anything. And just take a look at these examples. If an analyst sees the function set Windows hook XW, boom, a massive red flag goes up. That function is very often used to create keyloggers that record everything you type. See write file? Well, the malware could be planning to drop another malicious file. And open process? That means it's trying to mess with other programs that are already running on your machine. Each function is a huge clue to the malware's final goal. The next step, naturally, is to dust for fingerprints. Analysts use tools to pull out any readable text. We call them strings from the file. And these can be absolute gold mines. They can reveal anything from simple error messages to the web addresses of criminal servers, or even little clues about who wrote the malware in the first place. But here's the thing. Static analysis only tells you what the malware can do. To see what it actually does, we've got to move to phase two, the stakeout, or as we call it, dynamic analysis. Now, you obviously can't just run a virus on your own computer. That would be a complete disaster. So instead, analysts use a virtual machine, which is a totally isolated, sandboxed computer, as a kind of digital safe house. Inside this safe house, they set up monitoring tools to watch the files, the system's memory, the network, everything. Then, and only then, do they hit execute and watch the show unfold. A really crucial part of this stakeout is figuring out if the suspect is trying to set up a permanent base of operations. Does it try to make sure it runs every time the computer starts? We call this achieving persistence. A tool like Redshot is perfect for this. It takes a before snapshot of the system registry, which is kind of like Windows's central nervous system, and then an after snapshot to see exactly what changed. Let's look at a classic example of what Redshot might find. You can see it right here in the table. If the tool detects that the malware added something new to this run key in the registry, well, that's the smoking gun. The specific spot is one of the most common places for programs to hide to launch automatically at startup. The malware is basically planting itself there to guarantee it'll be back after a reboot. You know, malicious programs rarely ever work alone. They often have to phone home to a command and control server to get instructions or send back stolen data. To catch this, analysts use tools like Apache DNS. It does something really clever. It fakes an internet connection and then logs every single website the malware tries to contact, all without ever letting it actually connect to the real attacker. All right, we've examined the scene and we've surveilled the suspect. Now it's time for the final, most intense phase, the interrogation. This is where we break out a debugger to get the full story, line by painstaking line. So what's the most important tool you have in an interrogation? The ability to pause and ask questions. In debugging, that's called a breakpoint. An analyst can place these stop signs anywhere they want in the code. When the program hits that breakpoint, it just freezes, letting the detective look at its memory, its data, absolutely everything at that precise moment in time. Once the program is paused, the analyst has two ways they can proceed. They can step over a function, which is like asking for the summary. You let the function run and you just see the result. Or, for the really deep interrogation, they can step into a function. That means going line by line to understand exactly how it works from the inside out. It's really the difference between asking, "What did you do?" and demanding, "Tell me everything you did in order." But here's the twist. This isn't a case that ever really gets closed. The suspects are smart, and they know you're watching them. And this leads to a constant, escalating cat-and-mouse game. Malware authors have a whole bag of anti-analysis tricks. Their code might check if a debugger is attached, and if it is, it might immediately crash or totally change its behavior. It can look for tiny signs that it's running in a virtual machine and just refuse to run. And it often uses something called obfuscation, which is just a fancy way of saying it scrambles its own code into a nonsensical mess to make our job way, way harder. You know, this quote from the book Practical Malware Analysis just sums it up perfectly. It is a constant escalation. As soon as analysts figure out a new way to see what malware is doing, the authors invent a new way to hide. It never stops. Ultimately, this battle is happening every single day in real time. The digital detectives are constantly refining their tools, and the malware creators are constantly evolving their tricks. Which leaves us with a final question for the case file. In this high-stakes digital game of hide-and-seek, who do you think is winning?